In this video, I'm going to explain Gauss's law and electric flux. So what is Gauss's law? For now, you just need to know that Gauss's law is a tool that we can use to find the electric field, specifically of charge distributions where there is symmetry. Mathematically, it is written like this. But don't worry if you're not taking physics with calculus, because we're going to find a way to not use this calculus and get rid of this integral. But we will use a little of the language. And over the course of this video, we'll discuss everything we need to understand Gauss's law and make it make sense. We will need to understand symmetry, electric flux, and surface integrals. We'll begin with symmetry. There are three important types of symmetry that we'll focus on and take advantage of. These are planar symmetry, cylindrical symmetry, and spherical symmetry. An example of planar symmetry is a very large or even infinite plane or plate of charge. The electric field from this surface charge will be perpendicular to the plane everywhere. For cylindrical symmetry, we can imagine a charged rod or a charged cylinder. The electric field from the rod will move radially outward in all directions around the cylinder. The field will also be the same magnitude in all directions. Finally, there is spherical symmetry. We can imagine a point charge or a metal ball of charge where the electric field again moves radially outward, but now in all directions around the sphere. For the plate of charge, if we imagine creating a new plane any distance above the charged plate, every point in that new plane will have the exact same magnitude and direction of electric field. We can define any number of these planes as long as they share the same orientation as the charged plate. Similarly, we can create a cylinder around our charged rod. Because every point on this new cylinder is the same distance from the rod, each point will have the same magnitude electric field, and the electric field will always be outward. And again, there are an infinite number of these cylinders with each having a different radius. As you may have guessed, we can do the same thing with our ball of charge by creating a sphere that shares a center with the ball. Notice all of these surfaces, the plane, cylinder, and sphere that we're imagining around our charges are just that, they're imaginary. This will be important later. Another way to think about symmetry is in terms of operations or transformations that don't affect the result. For example, if we translate the plane left or right, our field doesn't change in magnitude or direction. The same is true if we rotate the cylinder along the axis running end to end through its center, or rotate the sphere in any direction. We can also make slices through each of these shapes where both sides look the exact same, and this is called a mirror symmetry. Now let's talk about electric flux. Flux in general can be thought of the flow of something through a surface or area. So air flowing through the area of a window could be thought of as air flux, for example. Similarly, electric flux is the amount of electric field passing through a surface or area. We'll denote electric flux with a capital Greek phi and use a subscript E for electric flux. This is because we'll eventually have magnetic flux later. We'll take our plate of charge producing an electric field straight up as an example. A surface placed above the plate will have electric field lines passing through it. When the surface is perpendicular to the electric field, a lot of electric field lines are passing through. But we can imagine rotating the surface. Now the cross-section the field lines can pass through is smaller. When the surface is parallel to the electric field, this cross-section is zero since our surface is only two-dimensional, meaning it has no thickness. We can think of the area as having a direction that faces perpendicular or normal to the surface. When this normal direction aligns with the electric field, the maximum amount of electric field passes through. And when the normal direction is perpendicular to the electric field, there is no flux. The electric flux will depend on three things. First, the direction of the surface relative to the electric field. Second, it will depend on the area itself. If the area is smaller, some of the electric field will pass beside the surface but not through it. And finally, it will depend on the strength or magnitude of the electric field. If there is less electric field to begin with, then less can pass through the surface. And we often use many field lines close together to represent a strong field, or field lines spaced far apart for a weak field. And if we did this, more arrows would penetrate the surface for a strong field and less for a weak field. Now we can use these to get an equation for the electric flux. Electric flux is the electric field times the area. Specifically, it is the electric field that is perpendicular to the surface times the area, since only the portion of the field normal to the surface makes it through. Using the angle theta between the electric field and normal to the plane, we can get the field perpendicular to the surface using cosine. Notice that if we treat area as a vector, this looks exactly like the dot product between two vectors E and A. And we can in fact write it this way. Now we have the electric flux for a constant electric field. Let's look more at expressing the area A as a vector. We'll draw the vector representing area in a direction perpendicular or normal to the surface. It wouldn't make sense to pick a direction along the surface or parallel because there are infinitely many to choose from. If we rotate the surface, the area vector rotates as well to remain perpendicular. We don't usually think of area as a vector, so we can separate the vector into its magnitude and direction. The magnitude will just be the number a representing the size of the area, and we'll multiply it by a unit vector which points in the direction normal to the surface. Now let's look at the electric flux through a surface when the electric field is not uniform or not the same size and direction at every point. To do this, we'll break up our surface into little patches of smaller areas. We'll use this little squiggly delta to represent a small amount of something, in this case area. I'll only draw 3 of these small area patches, and I'll label them with an index I, J, and K to distinguish them. At each of these points, the electric field may have a different magnitude and direction. So the flux through one of these small patches is the perpendicular component of electric field at that patch times the small area vector of that patch, which again we can represent with a dot product. Now, to get the total flux of this entire surface or entire area, we just need to sum up the electric flux through each small patch of area. And if we take the limit where the size of these small patches gets infinitesimally small, we can replace our sum with an integral. Now, this is a surface integral, and it is also valid for curved surfaces as well, but in general it may not be easy to evaluate. However, we're going to find a way to make this surface integral easy to evaluate. Imagine that our electric field had the same magnitude at every point on the surface and was also perpendicular to every point on the surface, even if it was curved. Since the electric field is perpendicular to the surface, it is always parallel to the area vector, so the dot product is just E times dA. Since E is constant, it will just come out of the integral, and we're left with just the integral of dA. But if we integrate or add up all the small areas over the entire surface, we just get the total area. So if these conditions are true, the electric flux is just E times A, the electric field times the area, which is extremely easy to evaluate. No calculus needed. Remember these symmetries I showed you before? All of these are examples where these conditions are true. The field from each charge distribution is constant and always perpendicular at these blue surfaces. Now that we know how to handle flux through a surface, we're really only interested in closed surfaces. A closed surface is like the surface of a box or a sphere or a cylinder. They are hollow, but closed so that you can't get inside them. Let's take the surface of a box, for example, and imagine we had a positive point charge at the center. Then the field would point outward through every side. We'll call this positive flux since it's as if the flux were coming from a positive charge enclosed in the surface. If we had a negative charge instead, the field lines would point inward through every side, and we'll call this negative flux. Now imagine we have the case where on 3 sides we have field lines coming into the box and the same amount of field leaving the box on the opposite 3 sides. Since we have the same amount of positive flux and negative flux and we're looking at the box as a whole, the net flux is 0. This is sort of like having a positive and negative charge inside, both producing the same amount of flux but in opposite directions. And since the net charge enclosed is 0, the net flux through the surface around the charge is also 0. Also, for a closed surface, we always define the direction of the area of that surface to point outward. And doing this gives us results that are consistent with how we've just defined positive and negative flux. When E and A are in the same direction, flux is positive, and when they're in opposite directions, the dot product is negative. Also, when integrating over a closed surface, we put a little circle at the center of our integral sign, just in case you notice they look a little different. Now we're finally ready to understand Gauss's law. Gauss's law states that the electric flux through a closed surface is proportional to the charge enclosed in that surface. Specifically, the flux is equal to the charge inside divided by epsilon naught. And as we saw, if we can make the flux easy to calculate, we can just set it equal to the right-hand side of Gauss's law. There are a few things to keep in mind. Gauss's law applies to closed surfaces, so not just a flat sheet or planar surface, for example. These surfaces are often called Gaussian surfaces, and they're not actually physical surfaces. They're more mathematical, but they allow us to solve for physical results. And finally, we use Gauss's law when there is symmetry, like for the geometries we saw before. Gauss's law would still be true without symmetry, but evaluating the integral to find electric flux could be a nightmare. Let's look at the simplest case to see how this all works. We'll use Gauss's law to find the electric field of a positive point charge. The first step is to use symmetry to determine the shape of our Gaussian surface. It should match the symmetry of our charge distribution, or in this case, the symmetry of a point charge. A point charge produces a field radially outward in all directions, which is a spherical symmetry. So our Gaussian surface will be a sphere surrounding and enclosing the point charge. The sphere will have a radius of little r, and if we take any patch of our Gaussian surface, we'll see that the electric field will be perpendicular to that little patch of surface. And since every point on the surface is the same distance r from the point charge, the magnitude of electric field will be the same as well. Looking at Gauss's law, the flux integral simplifies to just the electric field times the area, and the charge inside of our surface is just the point charge q. Since we know our spherical surface has a radius of r, the area is just 4 pi r squared. Now if we solve for the electric field, we find the same result for the field of a point charge that we get using Coulomb's law. I'll quickly make some comparisons between Gauss's law and Coulomb's law. Both give the same results for many cases, such as for the stationary point charge we just looked at. However, Coulomb's law isn't perfect. The limitation of Coulomb's law is that it isn't valid for moving charges, so we primarily use it in electrostatics where charges are still. Coulomb's law isn't entirely incorrect for moving charges. It can still be a good approximation as long as the charges are moving much slower than the speed of light. Gauss's law is easier to use for continuous charge distributions where there are symmetries, and it's also valid for moving charges. So in a way, Gauss's law and Coulomb's law mean the same thing, or they tell you the same thing, but Gauss's law is more fundamental in a sense, and it's more generally applicable. We'll go over more examples of Gauss's law in a future video, but that's it for this one, so I'll see you in the next video.